I think with the distinction of coming the farthest, I'm very happy to introduce Martin Nicholls, the Senior System Administrator from the University of Queensland in Australia, with their new Research Computing Center, who will talk to us about his experience using PBS Professional hooks. Please, welcome.
Thank you. I'll be talking about how we at the Research Computer Center use our PBS hooks to solve some of our site's problems. But first, I'll tell you a little about the RCC, the Research Computer Center, because it's only existed since the beginning of this year. So we provide high-performance computing services for the University of Queensland, and we also host the Australian National Computational Infrastructure Specialised Facility for Bioinformatics, and we co-host the Australian EBI mirror of bioinformatics data, and currently we are also a partner in building the Australian National Research Clouds for Compute and Storage. And we also do have a few other members of staff attached to other e-research projects. So we have a 378 node SGI cluster with Knasus parallel file system and about 3 petabytes of HSM storage. Our clients include local university researchers, regional researchers from our partner universities around the state, and then national researchers through the specialised facility and also through the CSIRO research organisation. So we have several funding providers, and each one of those has their own policies and requirements. And these differences include who can use the machine, the types of applications, and the types of reporting that they need. We have, I think, approximately 160 different applications on our system, but mostly they are bioinformatics applications. Our clients have a wide variety of computing expertise. We do have some very experienced bioinformatic programmers, but we have many clinical researchers and postgrad students who have no Linux experience and don't particularly want to learn that because it's a minor part of their job. Some of our clients have batch scripts that come from other HPC sites or their own cluster, and we have a relatively small support team. We have managed to grow that a little bit over the year, but we do need to make our support as efficient as possible. So I'm going to introduce you to some examples of how we used hooks to solve some specific issues, and then some of the techniques that we used within those hooks that might help you to get started on your own hook if you haven't done so already. As I said, our cluster was jointly funded, and each group has different reporting rights. So some of our researchers, particularly if they come from the university, they have research that may be sponsored by multiple different stakeholders. Some may come under the university share, some under the state share, and some under the national share. So we need to report that usage on a project basis rather than just a user or user group basis. We use the PBS Pro count string, and we've written a hook to make the use of that string mandatory. The count string is not used by PBS itself, but just retained in the jobs for job accounting records, and then we have our own accounting scripts that use that information. So our hook can check that any given that count string is a valid project, check that the user is a member of that project, or if the count string is not set, then for most of our users who only have one project, it will set it. Otherwise, if they have multiple projects, it can reject the job and ask them to provide it. We also, for new users who haven't yet been registered, allow them to run some small jobs. So we also tested job size. So in our implementation, we maintain the project membership within the Unix group database. So projects are a subset pattern of the group names, but the hook script itself uses a pre-extracted project file so that we minimize any delay in reading the group database. This is the main body of the code, which you probably can't read at all there, but I just wanted to show that quite a bit of logic can be achieved with only a few lines of Python. There are, of course, a few functions that are not shown here, but they're also quite short. Our second example is to help validate a local PBS custom resource. So our cluster is made up of several different types of nodes. These differ by their internal architecture and speed, as well as by the memory and disk sizes and CPU count. So we created a custom resource node type that identifies the base node configuration. And then clients can use this to ensure their parallel MPI jobs run across a homogeneous set of nodes so that they remain in sync, or they can use it to ensure their job obtains repeatable performance when they're doing benchmarking or scalability tests. Now, initially, our users experienced some errors using this custom resource. Typically, they entered the resource value with the incorrect text case, or they misspelled the value or invented their own values. And these jobs were then delayed, waiting on the queue, or in some cases when the resource name was text case was incorrect, the job was accepted, but the schedule would just ignore that particular resource. So in this hook script, it's a little bit more complicated because it has to handle resource requests in both the new select form and the older job wide form. So the code's a little bit more, but the hook script can correct the incorrect text case and reject any unrecognized values. I'll show a bit in a later slide how this corrected select string is regenerated during the same parsing phase, so the Python code remains fairly compact. Our third example is we wrote a hook to generate some custom scheduling resources. So our cluster runs a diverse mix of job sizes, CPU counts, memory size, and run length. We also have quite a diverse service level requirement. So some of our jobs are generated by web pages and require very fast turnaround. We have several categories of very large jobs where the users expect to wait a little while. And then we have very large numbers of small jobs, mostly in job arrays. So after trying several scheduler configurations, we found that some jobs were always disadvantaged and had poor wait times. So we chose to use the CPU hours, as shown in the PBS Pro admin guide, as a useful metric that could identify quite a wide range of our larger jobs. The CPU hours is just a product of the number of CPUs requested by the wall time. But we've modified it so that for large memory jobs, they're assigned a CPU figure based on their proportion of our local hardware. So for example, our large nodes have 32 CPUs and 1 terabyte. So a 500 gig job would be assigned 16 CPUs for this calculation. This CPU hours is then used as the highest weighting term within a custom job scheduling formula. So this helps ensure that each scheduled cycle, the large jobs are considered and given resources before they're consumed by the many smaller jobs on our system. The CPU hours metrics has also become the basis for managing equitable use across the cluster. So we set set it as a maximum 1 resource, so that users can either have one very large multi-node job or a smaller number of nodes running for a long time. The second scheduling resource is the scheduled minutes for a job. This was designed to help manage access to complete nodes, usually 8 CPU nodes. So jobs requiring all 8 CPUs on a node will experience delays. And in particular, jobs requiring several complete nodes often just sat on the queue and provided support people to assist before they would run. This occurred because our nodes were seldom idle. Jobs on node would terminate randomly across the nodes, so many nodes would have free capacity, but typically, before they became totally free, another small job would start on them. We tried other configurations, such as reserving jobs in queues for parallel work, but this only worked for short term and required a lot of intervention. The schedule minutes is simply the job duration in minutes, set directly from the wall time request. And then for nodes running our longer jobs, the node value is regularly updated to the duration until the longest job on that node is due to complete. So this ensures that these nodes will not accept jobs with a duration past their current busy time. The nodes will continue to accept shorter jobs so the resources don't remain idle. This provides a mechanism that guarantees all CPUs on a node will become idle simultaneously at a finite time. And this has been very successful in reducing the wait time for jobs requesting all 8 CPUs per node. And in particular, we now no longer have to intervene on large multi-node jobs. This also assists the rollout of software updates, which is helpful for me, by ensuring that all nodes will become idle within a finite time. Our third job scheduling resource is still a development project. It hasn't been completed mainly because the demand for it has disappeared and other things have been high priority. So this was designed to assist the management of special resources, such as our largest nodes or nodes with extra disk space or extra memory. We wish to ensure that these special resources are available as soon as possible when specifically requested, but we don't want to hold the nodes idle. So the job scheduling class identifies any job that requires special resources. And separately, it identifies small jobs that may run on any resource without significantly delaying their availability. So jobs, generally small jobs that with short run times. Each node then has the scheduling class set to the list of jobs, of types of jobs it will accept. This is similar to the queue list mentioned in the PBS admin guide. Now I'd like to introduce you to some of our fragments of code that we found useful. This is the first bit which we always put at the top of our hooks, which is just to enable us to run tests on the live server, because even if you run tests somewhere else, you need to do your final tests on the server where you've got those resources. So that always appears at the top of all our hooks. This is a batch script that we've written, which we use as a wrapper around QSub. So it just stays stored in user local bin QSub. So users by default obtain this rather than the PBS version. And what this just does is it prints out any job comment that comes from the job submission onto the user terminal. So then the hook script can use the job comment as a mechanism for providing user feedback. So in several of our scripts, we want to provide a message to the user but still accept the job. So we may want to provide a notice that their job has been modified, or we want to provide a warning that their job will run for an exceptionally long time, or other advice like that. We accept the job, but the user then has the option to delete the job if they decide, or they can just use that advice for their future jobs. This is just the outer logic, generic outer logic for most of our hooks. So it tests for the two types of resource requests, the select statement or the job wide. On the next slide, I've got the code to parse and disassemble. In the bottom of it here, we just gather up these resource name and value pairs, and we generically save them into a Python dictionary structure, so that the actual code, logic code, can be quite separate and done later. This is the parsing a select string, and you notice that as it parses through, it also rebuilds the select string in cell 2. So at the end of this, we have a new select statement, and then further down we can compare if they're the same and only need to modify the job if there's a difference there. Now, most of our hooks are only handling the QJob event. In general, our users rarely modify their own jobs. So a modified job event comes from either the system itself or from our support staff. So we've chosen not to validate any job modifications. However, we do need to reevaluate the scheduling values when a job is modified. So in that case, we do handle the modify job event. This is the code to handle that. We've moved the request value reading into a subroutine, and then it's just called twice. First with the event job object, and then if it's a modified job, we call it again to fill it with the rest of the request values that aren't being changed. where are we going with this? Well, we're moving towards a more generic script and a more generic job validation script, certainly. We have a new script that is in production. This validates the jobs resource requests both individually and as a whole, comparing it against resources available within each set of our local nodes. So this prevents acceptance of jobs that can never be satisfied on our cluster. This script can also do some other fancy things. So it can adjust the amount of memory requests so that if the user specifies the nominal node memory, which is usually 24 gig, then this can be adjusted down to the slightly smaller figure that the operating system sees. So, which I think is on our system is about 23.7 gigs. So currently that script is in production, but it only supports one chunk in the select statement. So we've seen that PBS Pro hooks can help validate user job requests against our local requirements. And they can certainly help reduce the number of jobs with errors and so help improve the user experience. And we have found them to be quite a powerful mechanism to implement our site changes that we require. Thank you.